Hello everyone, welcome to the live interaction session of the mathematical methods in physics. So this session will be hosted by me. I'm Biju Shaha from ISA Tirupati. I'm a Prime Minister Research Fellow. So the interaction session will be as follows. So basically in this session I will discuss few problems which are related to the topics that were being discussed in the previous week of mathematical methods. Then the session will be mainly of 2 hours, so it will continue from now until 2 hours from now. Then I'll present you with a few problems, and before heading out to solving the problem, I will review the concepts which are required to solve the problem, so that you can also approach towards how to solve the problem, and then we will together help in together cooperate in solving the problem. So in this session I will cover such 10 problems, and it will be it will be based on almost all of the topics which are covered in the week 1 lecture series of mathematical methods in physics. So let's continue with the session. Yeah, I hope to make this session interactive and fun in general. But since this is a pre-recorded lecture, because the live session that I conducted on Sunday, that is 28th January, I had faced a technical glitch. Because of that, I am pre-recording this session for the benefit of the students who would like to review the session later. So let's start with the session. So the first problem is as follows. So the first problem goes as, let me first read the question and then I will try to explain what the question says. So the first question goes as follows. So using vectors, we have to check which of the following statement is true. So the statements are as follows. First of all, it is say that the diagonals of a parallelogram they bisect each other. So usually by parallelogram we mean two opposite sides are parallel to each other. So this is the opposite sides which are parallel to each other, and this is the direction of the vectors. So if I were to write denote them it as A, B, C, D, so AD and BC, they are parallel to each other, and DC and AB are parallel to each other. So we have to show that the diagonals of a parallelogram they bisect each other. So if I draw a diagonal from one corner to the other, so BD is one diagonal and AC is another diagonal. So what this question essentially means, that we have to check whether the diagonals they bisect each other or not. That is, whether if the meeting point of the diagonal is, let's say, P, then whether AP is equal to PC and PD is equal to PB. So that is what we have to check from this, and all this the method which we'll use to check this is based upon the rules of the vectors that we are going to discuss in few minutes. And let us go now to the next statement. What the next statement is with respect to a triangle. So we have a triangle. So let me denote vectorially as the edges as AB and AC. These are the edges of the triangle, and we have to prove that the line segment joining the midpoints of the two sides of the triangle. So if AB and let's say CB are the two such sides whose midpoints are given by P and Q. So we have to prove that the line joining the midpoint, that is PQ, is parallel to the third sides, that is PQ will be parallel to the AC and it will be half of its length, that is PQ is equal to half of AC. So this is something we have to prove from this particular question, from this particular statement, using the rule of vector. So let me go to the next statement. So the next statement is again a parallelogram, But right now the claim is to prove that the two lines from one corner, so we let this be one corner, so we have to draw two lines from here, and they they connect the midpoints of the two opposite sides. So let's say this is the midpoint of this side, like if I were to distinguish them by vectors, so A, B, C. So a line originating from C crossing the midpoints of AB, that is P, and a line originating from BD crossing the midpoint line originating from C and coming to the midpoint of BD, let it be Q. So it is being asked to prove that these two particular lines, they trisect the diagonal AD. So essentially we have to prove, let's say they trisect at points say M and N, then essentially we have to prove AM is equal to 1/3 of AD. So this is the claim from the statement C. So we have to prove it using the rule of vector. And then the next step, next statement is that again we have a parallelogram. So in this statement we have to prove that we have a parallelogram, and the sum of squares of the diagonals of a parallelogram. So let this be one of the diagonal and let this be the other diagonal. So we have to prove that BD vector square plus AC vector square. So this is the sum of squares of the diagonal, and we have to prove this equal to twice the sum of squares of two adjacent sides, that is AD square plus AB square. So these two are the adjacent sides. So this is what we have to prove vectorially. So let us go about like at least verifying few of the statements of this particular question. Yeah. So these are the points that you need to keep in mind while you like proceed towards solving the question. So the very first concept is the triangle law of vector addition. So that is something you need to keep in mind, because all the steps will involve this particular property. So triangle law of vector addition says that so if there is a point and the two vectors originate from that particular point, that is this will be known as the head. So let's say A is the head of the vector and B or C are the tail of the vector. So in that case the resultant of this, that is AB plus so let us form the triangle first. So it will be as the resultant of AB plus BC will be equal to AC. So we have a vector whose like head originates from the tail of the other, then the resultant will be connecting the head of one and the tail of the other. So AC is that particular vector. So this is the triangle law of vector addition. Now the next concept is the case of parallel vector. So in case of parallel vector, suppose we have a vector, suppose we have a vector, denoted it as A. So and any other vector which is parallel to this vector, let's say this is that vector. So the magnitude of this vector, we obviously know that every vector has a direction and magnitude associated to it. So the direction of this vector is same as the direction of this vector A, but its magnitude is not the same. Since it's smaller in length, it would be some fractional multiple, some multiple which is less than like the factor multiplying it to the vector A will have a value which is less than 1. So let that value be alpha. So this vector will be denoted by this form. So it is parallel and the magnitude is scaled down. Yeah. So if the vector happens to be longer than the original vector, then this alpha will have a value greater than 1. Here alpha is less than 1. Yeah. So the next condition is the linear independent nature of vectors. So we say that the A and B vector, they are said to be linearly independent if we can represent it in this form, provided that this second condition is also met. So what this essentially means is that suppose you have two vectors A and B, and they are linearly independent, then that would mean that you cannot express one vector in term of the other. So that is saying that you can't write A as some multiple of B. So this particular thing is not allowed for the case of linearly independent vector. So writing this statement in a more elaborate way would be as follows. So it would be like, let's say we have this first condition which is satisfied by this linearly independent vectors. Then the second condition is also very important because you can easily say that okay, we can write this, so then it becomes again a linearly dependent vector. But actually that cannot be the case, because we again claim that both A and B has to be 0. So when denominator is equal to 0, this particular expression becomes undefined. So that is not a valid way to express A in terms of B, or in other words, A cannot be expressed in terms of B. So that it is required that both of these conditions are simultaneously hold good for the linearly independent vectors. Yeah. So right now let us go towards solving the problem which was stated in the first question. Okay. So the first question says the diagonals of a parallelogram they bisect each other. So let me go to the first question. Yeah. So yeah, let us work this particular statement here. Suppose we have a parallelogram which is denoted as this is our parallelogram, and let's say these are the diagonals. Yeah. So in our case, since we have defined the edges by mainly two vectors A and B. So any vector in this plane lying in the same plane as A and B. So A and B defines a sort of a plane, a two-dimensional plane. So any vectors lying in this plane can be expressed in terms of A and B. So that is what our motive is. So once we have defined the A and what is our A and B, so now let us write the diagonals in terms of this A and B. So first of all, let us focus on the diagonals BD. So AB plus BD is equal to AD vector. So that says that AD vector is equal to, sorry, we are trying to express diagonal, so that would be like BD vectors. BD vectors would be equal to AD vector minus AB vector, which in other words is B vector minus A vector. So this is my one of the diagonal. Suppose now let's say that both the diagonal intersect at P. Then in that case my BP vector would be equal to, since BP lies on BD itself, that means they are parallel, so they will have the same direction as BD, but it will be some fractional multiple of BD. So that is something which we discussed for the case of parallel the concept regarding parallel vectors. So this is my final form of BP. Now let us try to express the another diagonal again in the same kind of form. So another diagonal in this case is AC. So I would write AC is equal to AD plus DC, following the triangle law of vector addition. So that is B plus A vector. So that again using again the same criteria which we used for expressing the other diagonal, so we can write AP vector as some fractional multiple of AC vector. Yeah. So right now we have expressed AP and BP in terms of B minus A and X and Y. So the next thing would be to find the value of X and Y. So remember we had to prove that both these diagonals, they bisect each other, or in other words we had to prove that if this was condition was true, then X and Y should have come out to be equal to half. So essentially we have to find what is X and what is Y. So now let us look for some kind of known equation that would guide me towards finding X and Y. Since it is like two variable case, so we have to look for something which gives me two equations. Then I can use the two equations simultaneously and solve for X and Y. So one very important tool we have in hand right now is to write AB vector equal to AP vector plus PB vector. This can be written because using this small triangle, we can write as AB vector is equal to AP vector plus PV vector. So that can be written like this. Now let us express it in terms of again B and A. So AP something was we found out from here. This is what we something got already. So let me write. But BP vector is minus of BP vector. It is in a reverse direction. So minus of BP vector, and BP vector is given by this. Yeah. This is what we obtain. Now, and AB, we already know it to be A. So let me replace this with A vector. So this is what I have replaced my left hand side with, and right hand side has become this. So let us manipulate a bit, and then we can write something as A vector is equal to, let us separate out A component because that is one independent vector, and another component which is a vector which is along the B. So we have separate out two components right here, and it can be written as, from this day we come to here. Yeah. So now comparing both sides, you can match the coefficient on both sides and conclude that x plus y is equal to 1 because there is a 1 attached here, and y minus x is equal to 0. So that brings me down to solving simultaneous linear equation in two variable. So right now we have x plus y is equal to 1 and y minus x is equal to 0. This is what we got after comparing both sides. So immediately from the second we can conclude y is equal to x and using this in the first we can get x equal to y equal to half. So that is how we initially started with. So so a b c d. So I have initially I assumed bp is equal to some fraction of bd vector, so that x came out to be half of bd, and the next thing again it came out to be ap vector to be y of ac vector, it is half of ac. So this is the result that we obtained from this particular statement, and we actually proved that the first statement, which was this came out to be true. Now I will repeat like a similar kind of calculation for the second option. So let's proceed with that. So in this statement, what we have to look for is a triangle. So let's say this is a triangle. So these are the three vertices of the triangle, and let us connect the midpoints. Just connect the midpoint, and this time we have to prove that check or prove whether PQ is this claim true or not. So this is actually you can easily solve it by following this vector addition method. So one thing is to first find a basis vector, that is some two vectors that will define the plane. So those are called the basis vector. So everything else can be expressed in terms of those two particular vectors. So let me define AC as vector A and AB as vector B. So my AC is vector A and AB as vector B. So once I have denoted this, then I get to write CB is equal to AB minus AC, or in other words B vector minus A vector. Also we have that let us draw a line joining these 2 points from one vertex to the midpoint of the other. So in that case what we can write is AP vector plus PQ vector is equal to AQ vector. Yeah. So AQ again can be written as AC vector plus CQ vector, and CQ vector is actually half of CB vector. So AC is vector A and CQ is half of CB, that is half of B minus A. So that was the thing with the right hand side. Now let us focus on the left hand side. So AP is again, it is half of AB vector, so half of B plus PQ is something we don't know. Yeah. So from this particular step we can easily write that PQ is equal to A vector by 2, because this particular cancels with this, and only PQ is equal to A minus half of A, which is half of A. So A was, remember, AC. Yeah. So this was the claim. So the line segment joining the two midpoints indeed came out to be parallel, so they have the same direction, but the magnitude is half of the base vector AC. Yeah. So in this way we actually proved that even the second statement is true. Similarly, you can also carry out a similar analysis for the C and D option. So in this case, again, in both the case, again we have a parallelogram. So again, choose a suitable basis, suitable two vectors that would define your plane. So in this case, you can choose these two as your basis vector that will define the plane, and express every other vectors that are needed in this problem. So the third problems needs this kind of vector. So you can easily express this and this in terms of the basis vector, and try to find out again a relation solving which you can get the value of this unknowns. So here you have to find whether this part is 1/3 of the entire diagonal. So again, that is analogous to the first part, so you can easily do it out. Again, the second problem, the fourth problem can also be solved by a similar approach. You have to show that the square of the adjacent side is sum of squares of the adjacent sides is equal to sum of squares of the diagonals. So problem 1 can be easily proceeded, and you can check whether these statements are true or not. So that is with the problem 1. So this is what I have actually done, and like the same thing I did in the rough work, so I'm not going to go again into this. So let us now discuss about the second problem. So in this problem, basically you have to show that you have a three-dimensional vector. So three-dimensional vector is something we always come across in physics. So there is a x direction, y direction, and a z direction. So this is your x direction, this is your y direction, and this is your z direction. So this is a three-dimensional plane. The components, like let's pick up any point in the plane. So the component is they are actually complex. So the numbers here can be 3 plus 2i or similar, like the individual complex individual coefficient ax, ay, az, they are all complex components. So which of the following statement is true? So again, we have to check which of the following statements are true. So the first statement claims, so to find actually all of this in this fourth statement, you have to find out are they forming a vector space or not. So you have a set. So set is a collection of elements. So for this particular cases, so if I denote these vectors as just by their components, so ax, ay, and az, they are all complex values. So they all belong to the complex plane. So then there are various subsets in the question from this particular set. So S1 is with az equal to 0, and ax and ay can take any complex value. So that is with the first statement. And so this particular things is a special case of this. So this is a subset S1. So we have to prove whether this subset forms a vector space or not. So that is with the first. Now the second option is again like if we replace az with 1, so again is this subset a vector space, or if all of these are equal to or has equal component, that whether even ax, ay is ax and az is even ax, so whether that forms so that will become a third subset. So whether that subset forms a vector space, or if they have some kind of relation between some kind of relation like this, so in that case whether it consists of a vector space or not. So essentially you have to check one very important thing is how to verify whether a set forms a vector space or not. So for that, let us go into the definition of the vector space. So what are the points that you need to keep in mind whether to check whether a subset forms a or a set forms a vector space or not. So let us start with a set of vectors given as follows. So this is a collection of various vectors. So in our case, all of these the components, so in our case these are individual ax, ay and az. So there can be any other complex number, ax prime, ay prime, az prime. So all these are these are the, in our case, these are the members of the sets. So in any general approach, let's say that this is the sets in the vector space. So we have to prove the following conditions. So you have to say that a set has to obey this particular 4 condition in order to form a vector space. So what are these 4 conditions? So first condition is something known as closure under vector addition. So an operation is defined, vector addition, that is being defined. So if you pick up 2 vectors from this set, any 2 arbitrary vectors from this 2 set, let us pick up x1 and x2, you could pick up any arbitrary vector from this set, and if under the vector addition, so if the resultant it falls in the same set itself, if it belongs to the same set from which the individual terms of the term belong to, then you say that this particular set obeys this first condition, which is the closure rule under vector addition. Similarly, the second rule is closure under scalar multiplication. So in that case, you have a vector, let's say any arbitrary vector picked up from this set, and right now you multiply a scalar to this vector. So every vector space is defined on a field. So in this case, let us and the elements they are known as the scalar fields. So if you multiply a vector with any member of the scalar field, the element has to lie in the set itself. So that is the closure under scalar multiplication. Now the existence of a null vector, that is because that has to be verified by this rule. Suppose you pick up any vector, so you have to perform vector addition with some vector which lies in this set itself, so that when you perform addition, the resultant vector is the same as the original vector. So you picked up an arbitrary vector and you performed an addition operation with some vector which is known as the null vector, and if you get back the same vector x which you originally started with, then that element is called the null vector, and it can't be any arbitrary element. It also has to lie in this set itself. So that says that yes, there is a null vector lying in this set. Now the fourth criteria is every vector you pick up, again any vector, has to have an additive inverse. So when you perform addition between a vector and its inverse, you are supposed to get back the null vector. So this is the null vector. So whatever null vector you started with, it could be a null matrix also if the set elements are 3 cross 3 matrix, or if it is for our case it has 3 components. So in that case, if the null vector is with all the components being equal to 0, if that is a null vector, so you have to get back that null vector when you add an inverse of an element to the element itself. So that is the criteria. So these are 3 criteria. First of all, you have to check whether it is closure under vector addition and scalar multiplication. That were the first and second criteria. And the third criteria is you have to look for the existence of a null vector. And the fourth criteria you have to check is every vector should have an additive inverse. So these are the four criteria. If all of them are satisfied, then you conclude that yes, the set of vectors, it forms a vector space. But if any of this criteria, any of this given criteria is not satisfied, immediately the vector space, the set fails to form a vector space. Then you can no longer call the set of vector as a vector space. Yeah. So right now, what we are focusing on is to form a vector space with this element. Is to form a set with this element and check whether the set forms a vector space or not. Yeah. So let us go about it. First of all, let us write the vectors. So if V was my original vector, this is your original vector. Okay, so all other cases are subset of this. So my first set was that let's say we want to be a subset of the parent vector. So in that case, the form is this. Remember, the third component has to be 0, and all other ax and ay, they can be any number. Sorry. So this is not real, so they can be any complex number. So this is the set which you have in hand. So right now you have to check whether all of the four criteria were they satisfied or not. So let us pick up A and B vector from this vector space. So obviously if I picked up from this, right now it is not yet established as a vector space, so right now it's just a subset. So I picked up A and B as two elements from this subset. So since it belongs to this subset, A and B should have a form like this. So this is a different vector with different component, but the third component is always 0. Yeah. So these are the two vectors. Now you have to check the first rule. The first rule says that the first rule was closure under addition, and the second rule was closure under multiplication. So if we combine them, so let us pick up any like scalar, any scalar I picked up and I multiplied it with a vector. So, and I can actually combine the first two rules. So if I perform this will guarantee my closure under, if this belongs to the same subset as V1, then I would say that it is closed under multiplication with a scalar. Similarly, B also has to satisfy this. So this also has to be in the same set as V1. So if both of them belongs to set V1, and if I were to add them, and if the resultant again belongs to V1, that means that it is even closed under addition also. So earlier individual term, if they belong to V1, would verify that it is closed under multiplication, and right now if I add, that would verify that it is closed under addition it's also. So let us check whether it actually belongs to V1 or not. So let us define it as these vectors as C. So once I put this form of A in this particular expression, what I get is alpha of . So this is what we get from this, and now let us separate out individual component. So individual component will be yeah. So some like prefactors would be there, but what we see is that so since ax and bx were complex and the alphas were scalars, so we can conclude that all of them actually be, individual components are also scalar, but the zth component is 0 again, because anything multiplied with 0 is 0. So this is non-zero, this is non-zero complex, but the third component is again 0. So what we conclude is that again C has a form which is same as A and B. So it belongs, C belongs to the set subset V1. So that verifies my closure property, which was the first and second property to be a vector space. So now let us go about checking for the whether there is any identity element or not. So the hand rule of checking whether there exists an identity is that, let's say we have an element and we pick up any vector from the vector set, then we are supposed to get back in any fashion. If you perform the vector addition, so you should get back the original vector. So in our case it was mainly ax, ex. Yeah. So you have to multiply with something so that you get back the, you have to add with something so that you get back the same thing. So since all of them are numbers, definitely the first claim would be yeah. So this is like the this is the identity vector. So this is the identity vector. Yeah, and it belongs to the set V1 itself, because these two are, they can be a special case of complex numbers where both the real and imaginary part are equal to 0, and yeah, we have to essentially check whether the third component is 0 or not. So yeah, here the third component is 0. So yeah, it forms a member of the vector set. So there every element has an identity vector which is given by this. So let us denote the identity vector as O, and it has this form. Yeah. So right now the next condition what I have to check is the existence of inverse. So that is, I have to find something like an inverse element, inverse vector for this particular element A, which will give me back this identity vector, that is this particular vector. So obviously the only valid inverse member would be to, like, suppose my A is denoted by this, the only way I could recover like the null vector from it is to add with something which has coefficients as a negative of the coefficient of the original one. Yeah. So given this, like we just change the signs, and then we could get, like when we add this vector to this vector, so what this particular vector to this particular vector, what we get is the null vector. So yeah, every element has an additive inverse. So this is 0. So for these cases, yeah. So this additive inverse is again a member of the, so the additive inverse for if there is any vector belonging to V1, so there exists a inverse which has been given by so that verifies the existence of inverse. So right now we have like proved all of these three condition holds good for the first option. So that confirms here the subset of all vectors with az equal to 0, they constitute a vector space. Similarly, the other conditions can also, other statements can also be verified whether it forms a vector space or not. They may not form a vector space, like in some option it may or may not form a vector space. That will be decided whether any of this criteria is is not met, or is any all of these criteria are met. So suppose you were to start with this first like a second example, and you encountered that it is not closed under this vector addition or scalar multiplication. So in that case you immediately confirm that it is not the subset do not form the vector space. Then you don't need to go back to the go to the further options. You can do it, but it's once the first condition is unsatisfied, so the remaining conditions do not hold much importance. So that says that that particular subset do not form a vector space. So you can check B, C and D and confirm whether it forms a vector space or not using the same way I did for the option A. So this is what I just did right now, so I'm not going to read this. So problem 3. So let us come to this particular problem. Here you have to check which of the following collection of polynomial constitute a vector space. So polynomials are functions, so with some degree. So given a polynomial of some degree, let's say if you have a polynomial of degree 3, then the general form of that is polynomial of degree 3 would be so all of these are like this a0, a1, a2 and a3 are the coefficients, and the degree is the highest power, that is 3. So this is a polynomial of degree 3. So it is said the polynomial of degree less than n. So that is in a condensed form if I write it, but I running from 0 to n minus 1. So that is a polynomial of degree less than n. So we have to check whether the collection of these polynomials with these coefficients are demanded to be complex, whether that set forms a vector space or not. Again we have to check all the 4 properties and see whether they form a vector space or not. Then the next statement says a special case. They say that even polynomials of degree less than n, that is this I, it can take only even values. It can start from 0 to 4, like it can take only even values. So that says that whether the even polynomial, like even the even polynomials, whether they form a vector space or not. And the third case is says that this polynomial of degree less than n, but at x equal to 0 the polynomial should attain a value 1, that is f of 0 should be 1. The special case of again this. So I've said meeting this with elements meeting this criteria, we have to check whether that is a vector space or not. So next D option is again the same. So in this case next option says that you have to check f of 1 is equal to 0. So earlier it was f of 0 is equal to 1, and now it is at x equal to 1 the value is 0. So that is, all these cases are like special case of the first one. So let me briefly describe how to explain the how to verify whether the first set forms a vector space or not. Then a similar procedure can be adopted for the remaining problems. So here I have the solution. So initially what I did is I wrote a set. So my V1 is the set. So here if the this is the expression of the polynomial with degree less than n minus 1, and then the coefficients are complex. This is the complex coefficients, and I ranges from like the coefficients can range from 1 to n minus 1. So let me check whether it obeys the closure rule of vector addition and scalar multiplication. For that, again I pick up two random element from the set. So I have named the random element as fx and gx. So these are my random elements, and they have this form. Yeah. So they have this form of fx and gx because they belong to the same set. Now I am multiplying two scalars to each of this each of this elements, each of this polynomial, and then adding it. So if this particular thing, alpha of fx and beta of gx, it belongs, if this particular thing also has the same form as v1, that is, it is again a polynomial with complex coefficient and degree less than n, that is if that is this particular summation, this particular resultant is again obeying that criteria, then it again is a element of v1. So let us check that. So in this case, this is how we write it as. So we have alpha, we just put the expression of fx and gx here, and yeah, since alpha, beta, ai, b are they're individually complex, so this particular coefficient, it turns out to be complex. So yeah, it can be written out in the same form. So that says that hx is also an element of v1. So closure property is satisfied. Now the identity property is, again, you have to add something so that you get back the original function. So the only obvious choice is add the value 0 to it so that you get back the original function. So it can be 0 is like a special case of this polynomial with all the coefficient a0, a1 up till an minus 1 is equal to 0. So since it could take any complex value, it is allowed to take value 0 also. So that confirms that identity element, this identity element exists in v1. So there is an existence of identity element as well. Now the second condition is inverse. Now third condition is inverse actually. So the inverse case is that you have to add some element to the function function fx so that you get back the identity element. So identity element was 0. So what is something that you have to add to get back 0? Obviously it is negative of the the coefficient. So in that case, this is what it is shown here. So the individual coefficients are negative of the original coefficient. So when you add them, you get back the identity element, which is 0. So yeah, every element has a inverse and the inverse lie in the set itself, v1. Inverse element exists in v1. So we have checked all of these conditions are met even for this subset which is being defined by this first statement. So that confirms that collection of all polynomials of degree less than n is indeed a vector space. Similarly, you can repeat the b, c and d by taking even polynomials and by imposing the c and d constant on the polynomial and check whether it forms a vector space or not by following the same three criteria. Now the next problem is again we have to check whether the set it forms a vector space or not. But right now the the elements are not polynomials or they are not like numbers, but they are matrices. So there are actually two sets which have been which are stated in the question. One set is a m cross n matrices with real elements. So what is it like? So let me denote the individual element of the matrix as m. So this is my one set, let P be that, and then this is the matrix such that P of ijth element of P is real. So that is the definition, and the order of this is m cross n. And the another vector, another set is the m cross n, again another matrix, but the individual elements are said to be complex. Yeah, these are the two vectors, these are the two sets. Now we have to check whether these two sets form a vector space or not. So it is upon a scalar field, so we are restricting ourselves to scalars with which we multiply the vectors to be real number. So remember, in closure application we were multiplying each vector with a scalar. So like let's say we take two elements from A, so two elements are P and Q, they are matrices, m cross n matrices. To check the first criteria, that is closure under vector addition and multiplication, we were multiplying with scalars alpha beta, and then we are performing addition. So by this statement, like restrict the scalars with which we multiply the vector to be real number, we mean to say that alpha and beta, they are real, even though the elements of the matrix can be complex, but that is the definition of the set. But the scalars with which we multiply is actually it has to be real. So with that definition, let us go forward. So I have done for the set A, which was m cross n matrices with real elements. So that is like vector A is m cross n such that the elements are real. So this is the definition of the set A. So let us pick up x and y from this A. They are again like m cross n matrices with real entries. Now z is given by this, alpha beta is real because it was mentioned in the question. So again, since individually they are m cross n matrices with real elements, and alpha and beta also turned out to be real, also like were said to be real in the question. So obviously this particular thing has to be entirely real. So Z is again an m cross n matrix with real elements. So closure property is satisfied. Now the next criteria is to check the existence of identity element. So again, if you have any matrix, and to get back the same matrix, that is 1 2 3 2 4 5, to get back this matrix we have to we have to add with something. So that something is essentially our null matrix. So that is what the criteria is here. So that says that the identity element also lies in the set itself, because it is an m cross n, so this row is not there. So m cross n matrix, so in this case it is like 2 cross 3, this is also 2 cross 3, and this also has elements, to individual elements to be real. So yeah, so the identity element also exists in A. So we also have to find additive inverse. So that what is the claim for that? Again, suppose we have a matrix 1 2 3 4 5 6, we have to add with something that gives back me the identity element. Yeah, so we have to get back this. So the only way to get back this is to add with the matrix whose individual element is negative of the element of the original matrix. So that is what I did. So yeah, again it is a 2 cross 3 matrix as it was for the original matrices, 2 cross 3, and yeah, the coefficients are also, they are also real, it belongs to real. Yeah, so like this, if you pick up any element, any matrix from the set A, then you will find a corresponding inverse element by just negating the coefficients, negating the elements of the matrix, and you can conclude that there exists an inverse. So all of the three criteria of the vector space are satisfied. Similarly, like this, you can check for the for the matrix so set B also, and verify. So in set B, what the claim was, the individual elements, they had to be complex. They can be they are complex. So it has to be 3 plus 2i 4 plus 2i 7i. So the elements have to be this form, so they can't be real. So that is what you have to keep in mind and verify whether set B forms a vector space or not. Now the second criteria is again like trying to find out whether this again a set of matrices, it forms a vector space or not. Right now again we have two set. One is this V1. So in this case we have 2 cross 2 matrix with complex entries. Yeah, so the entries are complex here. But right now the difference from the previous question is that the complex number forming the scalar field. So the alpha, beta, whatever we are multiplying, they are now complex. So that is the difference. And the V2 case is that 2 cross 2 matrix with complex entries. Again 2 cross 2 matrix with the complex entries. So basically both of them are same, they are the same set V1 and V2, but what makes them different is what the underlying scalar field is. So in this case the underlying scalar field was a complex number, so alpha beta had to be complex, but here the underlying scalar field is a real number. So in this case the vector operations or the scalar operation, whatever you are going to do on this vector field, the scalar elements are real, they are not complex. That is the difference. So this is an example of a vector field which has same vector field which has two different underlying scalar field. So how is the situation going to change, whether introducing a new scalar field makes the vector space makes the set not a vector space, or makes it a vector space? That you can verify by carrying out checking all the criteria, so the closure property, existence of inverse, and identity. By following that you can actually show whether they form a vector space or not. Yeah, so it can be done, so I'm not going to detail into it. It has the same prescription, so you have to check closure, identity, and inverse. So I'm not going to this detail. Yeah. Now let us so far we have discussed about this particular concept, so let me just review. So mainly question from problem 2 till 5, 2, 3, 4, 5, 4 problem were based on finding out whether a set forms a vector space or not. So that is what that was found out by solving this verifying these 4 criteria for a set, and if all of these criteria are satisfied, then it formed a vector space. If any of these were unsatisfied, then it is not a vector space. So the 4 problems were based on this. Yeah. Right now let me move to problem 6. So problem 6 is asking which of the following statement is true. So first before heading towards reading them, so let us look at the terms used. So one is the terminology is orthogonal vectors, and the other one is a linearly independent set of vectors. So these are the 2 terms that are being used. So let me introduce what are they. So linear independence I already discussed quite few minutes back. So this is the relation. So if there are n such vectors and they are linearly independent, then they have to obey this particular condition. So a linear combination of them with coefficients if the total resultant is equal to 0, then the individual coefficient, that then it implies that individual coefficients are 0. So if that condition is satisfied, then we say that the vector involved are linearly independent. So if they are not linearly independent, then they constitute a linearly dependent set, because then we can express any vector in terms of the other vectors. So that is like, suppose you have 4a1, 5a2 plus, so here what we have is this summation is 0 even though these coefficients are not equal to 0. So using this, what you can, only one coefficient is 0. So what you can do is you can definitely express a1 in terms of a2. So that is what, like, they are not linearly independent, but they are linearly dependent, because you can express one vector in terms of the other. Now the concept of orthogonal vectors. So you must have learned about something called scalar product. So if the scalar product or the inner product of the two vectors turn out to be 0, so these are the two vectors introduced. So if the inner product turns out to be 0, then we say that x and y are mutually x and y vectors are mutually orthogonal. So that is what it means by orthogonal vectors. Now let us look at the question. So the first claim is that a set of mutually orthogonal vectors may or may not be linearly independent. And the second claim is a linearly independent set of vectors need not be mutually orthogonal. So all other options is asking us to verify if one is satisfied, is the other satisfied, or the or is the reverse statement is also true or not. So let us first start with a set of mutually orthogonal vectors and check whether they have to be linearly independent or not. And the next next claim would be, we would start with a linearly independent set of vectors and check whether they are mutually orthogonal or not. Yeah, so this is what I started with. So I started with two linearly independent vectors. So a1 and a2 are two linearly independent vectors. So that immediately means this particular expression. So, and then the next step, since we are looking out to find, since we are trying to find whether they have to be mutually orthogonal or not, so we need a scalar product. So what we did, we multiplied both sides with this ket a1. So because we are trying to this a1 choice is completely arbitrary, you can start with a2 also, just that the final step would involve a little change, but it would conclude the same result. So this choice is completely arbitrary. So we multiplied both sides with this ket a1. So since inner product of a vector with vector itself is always greater than equal to 0, so it is equal to 0 only when a1, it is equal to 0 only when a1 is a null vector. Otherwise it is always greater than 0. So that says that we can replace it with some finite scalar. So this is actually scalar. So we can the final value. So finite value. So that is a non-zero finite value. So we wrote it as C1. So we replace it with C1, and then this condition brought us to this. But the initial claim was that alpha 1 and alpha 2 are individually 0. So the above equation is satisfied, this particular equation is satisfied even when this term is not equal to 0, because ultimately alpha 1 and alpha 2, they are individually 0, right? So even if they are not equal to 0, this statement holds good. If they were equal to 0, then also it's fine, it is not violating the expression. So that says that a linearly independent set of vectors, they need not be mutually orthogonal. They can be like orthogonal, but it's not a necessary thing. So the first claim is solved. Now the next claim was, we start with two vectors a1 and a2, and we start with them being orthogonal. So let us start with n mutually orthogonal vectors. So we are starting with such n mutually orthogonal vectors. So we started with n mutually orthogonal vectors, and we are claiming so the inner product of vector with vector itself is it can be any finite value. So let us take that value to be 1. So that is what it is written. If I equal to if I equal to j, that is inner product of a vector with vector itself. If it is it is equal to some finite value, which is 1. But orthogonal by definition itself means that like if there are n mutually orthogonal vectors, then like the scalar product with a vector with some other vector in the set would turn out to be it turned out to be 0. So that is what the definition is if I is not equal to j. If I equal to j, then it is 1. So now let us consider this equation. So this particular equation is a linear combination of all the vectors with some coefficient. So if I'm taking if I'm saying that claiming that they are linearly independent, then I should conclude that individually the coefficients are equal to 0. So let us check this. So what I do is I take inner product with any arbitrary vector from this set. From this n number of vectors, I pick one candidate and took an inner product. On both sides. So this is the expression I get. So in this, what I conclude, since now I impose this particular condition, so that says that all terms are 0 until when there is a term like this. So in this case, this is not equal to 0, this is equal to 1. So we are reduced to alpha m equal to 0. So now since this choice was completely arbitrary, the choice of vector am was completely arbitrary, we could have chosen anything in between. Suppose we have like 5 independent such vectors, 5 such orthogonal vectors. Yeah, so suppose we have 5 such orthogonal vector. Yeah, so I could have picked, let us pick m equal to 3 and show this and get alpha 3 equal to 0. Then equally I have the right to choose m equal to 2 and get alpha 2 equal to 0. So similarly I can obtain all other coefficients to be equal to 0 if this condition had to be satisfied. So using this for all arbitrary vectors in this set, we can claim that the individual coefficient had to be 0 if this statement was true. So that says that if n mutually orthogonal vectors is always linearly independent. So how to understand this, like these two concept is that using our parallelogram thing. So geometrically orthogonal vectors means two vectors which are at 90 degree. So our parallelogram, these two vectors, they were linearly independent. You could not explain one vector in terms of the other. That was never possible. So that says they are linearly independent, but they are not mutually orthogonal. So this angle is not 90 degree. Had it been a square, so if it is a square, then it could be 90 degree and keep staying linearly independent with respect to each other. So it is not necessary that they have to be orthogonal. But for the case of the second claim, it says that two orthogonal vectors. So let's take x-axis and y-axis. So they are linearly, they are orthogonal, but also they are linearly independent. You can never express x vector, the x-axis with respect to y-axis. So if they are orthogonal vectors, this is never possible. So if they are orthogonal, they have to be linearly independent. So that is what solves the claim of the question 6. Now let us come to problem 7. So in problem 7, what it has been stated is that suppose we consider the space of two-dimensional vectors in which both components are real. So it has been asked that to consider a two-dimensional space with both components being real. That means the axis, the values ax and ay, they are real. So this is bx and by, so they are also like real. So in that case we are asked to like find out if the definition of this inner product is actually legitimate or not. So is this the definition of scalar product allowed or not? So that can be so before going into how to solve the problem, let's first check what is the the scalar product of vector essentially means. So for the case of for a inner product or a scalar product, inner product and scalar product are essentially the same thing. So for a scalar product to be legitimate or for a scalar product to be like valid, it has to obey certain criteria again. Just like vector space had any set had to obey certain criteria to form a vector space, similarly any definition of like the scalar product have to obey some criteria. So these are the three such criteria. One is the symmetry criteria. So this inner product in general can be complex number. So by symmetry I would mean their Hermitian symmetry. So Hermitian symmetry essentially means that suppose we have this inner product, so whatever we obtain after performing this operation should be equal to this operation. So the change here is that the first element becomes the second element and the second element becomes the first element, and there is the conjugate operation on top. So that conjugate of the inner product of y and x should be equal to the inner product of x and y. So that is what the first condition is, and the second condition is the distributive property. So the distributive property goes as follows. Suppose you take a linear combination of two vectors of x and y belonging to a vector space. So x and y belongs to a vector space. So from this rule we can easily say that the z vector, this z vector, it also belongs to the same vector space because the vector space is closed under addition and the scalar multiplication. So z belongs to V. So and let us pick up any arbitrary vector, a third vector w. So x and y and w are three vectors. Now we have to find whether the inner product of w and z is given by this or not. So w is being distributed in x and y. So if this condition is satisfied, then the definition of the scalar product what we have is legitimate. So that this is the distributive law, and the other thing is the positivity condition. So positivity means the inner product of a vector with vector itself has to be positive, except the fact when the vector itself is 0, at that point it will be 0. So that is the positivity criteria. Yeah. So now let us look into what is the definition of the inner product in our case. So it is given that this is the definition of the scalar product. Now to check if this is a legitimate scalar product or not. Okay. So this in general it is the inner product. So if it obeys certain these three criteria, the inner product can be defined as a scalar product. So to check if the inner product is a scalar product, is a legitimate scalar product, we have to check this condition. One is the condition of Hermitian symmetry. So in this case it is, we have to check this is satisfied or not. But since in our case B and A are actually real, so the complex conjugate of a real number is the number itself, so we don't have to bother about this the conjugate sign anymore. So we have to check whether A dot B is equal to B dot A. So we just put A dot B is equal to AX BX plus half of AY BY, that is from this definition, follows from this definition itself. And second thing is B dot A. So B dot A is the first component is brought to the second, and the second component is brought to the first. So that is what is the change. So obviously the LHS is equal to RHS because individually they are all numbers. So since multiplication is always commutative, so we can say that yes, LHS is equal to RHS. So the first condition is satisfied. Now the second condition is the linearity. So the linearity condition is that regarding the distributive law, whether any arbitrary vector distributes itself to the linear combination of the vector or not. So let us check this. So we have substituted like AX and BX here. So that is from the definition of the A. So alpha AX plus beta BX, and this is the y component alpha AY plus beta BY. So this is just taking the X component and the X component of the linear combination. So X component of this linear combination is alpha X plus beta BX. That is why I have written the first as like this, and the second term involves the y component of C and the y component of this entire thing. So after rearranging all of this, it turns out that after rearranging all of this, it turns out that it indeed obeys the same definition, that alpha C dot A is equal to beta C dot B. So we could club out this CA terms and CB terms, and it forms the same form as it is given in the the inner product definition. So this is what is the condition. Now the next condition is the positivity. So positivity condition is we are taking the inner product of a vector with vector itself. So that is being written here. So both, even bx is ax here. So ax square plus half of ay square. So this entire thing is always greater than 0 because it involves square, and it is equal to 0 if a itself is a null vector. If both of them turns out to be 0, then this condition is equal to 0, but it can never be negative. So the positivity condition also holds good. So that verifies that the given definition of the scalar product is satisfied. The given definition of this inner product satisfies all the condition, and hence it is a legitimate scalar product. Now we come to something called Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality looks like this. Let me present first. So this is the inequality, how the inequality looks like. So there are two arbitrary vectors. These are the two arbitrary vectors. So taking the norm and then squaring of the inner product. So this is the inner product of x with y, and then we are taking, since it's a complex, so we take the modulus of it and then square it. So this is what the left hand side is. Right hand side is taking the inner product of a vector with the vector itself, and there, since we are dealing with two vectors, so we have this multiplication of two two such inner products. So Cauchy inequality says that the right hand side is always greater than or equal to the left hand side. So this is what Cauchy-Schwarz inequality looks like. So what we have to show is that, suppose my two vectors, so the two vectors in question, they are multiples of each other. So if they're multiple of each other, does the Cauchy-Schwarz inequality reduces to an equality, or what happens? Like what happens for if they are multiples of each other? So let us first verify that. So we started with this particular definition. So this particular definition goes as follows. So there are two vectors z1 and z2, and I have written them as multiple of each other. So and constant multiplying z2 is equal to z1 vector. So the z1 vector expressed as a multiple of z2, and then if I take a complex conjugate on both sides, this is how it transforms, as the bra becomes a kit and alpha becomes a complex, alpha is now a complex conjugate. So this is what Cauchy-Schwarz inequality looks like. This is what we learned from the previous slide. So let us check whether this equality becomes an inequality, whether this inequality becomes a equality or not. So let us first start from this RHS. So RHS is nothing but this. So this thing, as I said, this is like the modulus of the square. This particular things means multiplying a complex number with its conjugate, that is equal to the square of the modulus. So I have just expressed it separately here, the RHS. First term is the complex conjugate of the second term. So that is from the definition of the modulus of a complex number. And then we have expressed, we have used the definition of the conjugate of an inner product. So z1 z2, a conjugate is applied on this inner product, and then this is what it looks like. So it flips the position. So that is what is the next step. Next is we use the definition of our special case where z1 is a multiple of z2. So we just substitute z1 equal to alpha of z2 in the first step, and in the second case we substitute z2 is equal to 1 by alpha of z1. So after this we could immediately cancel both the term, both the alpha from, because one is the numerator and other is in the denominator. So we could cancel both of them, and then this is what it remains. So this is what our LHS was. So remember, this is what our LHS was. So right now we have proved that our inequality becomes an equality for this special case. So the special case here was involved with this definition of this very definition, where it was said that one vector was some multiple of the other vector. So for this very definition, our Cauchy-Schwarz inequality becomes an equality. Now there is a statement in the last that for the vector space of complex number for which the scalar product is defined as this, is the Cauchy-Schwarz inequality is always an equality. We have to find it. So what happens is, actually in complex field, suppose you have two arbitrary such complex numbers z1 and z2. They are like two such complex number, and in complex number you can actually relate two numbers, like to any such complex number by a coefficient, by a multiplicative factor. So the multiplicative factor itself turns out to be complex. So this is since a complex the complex plane, so we could have this coefficient to be complex. So we can easily find out what is alpha from this. So always in terms of for the case of complex vector, complex number, we can find out a complex number that would help the two number to be expressed as as a multiplicative power of the other, as a multiplicative factor of the other. So with that freedom, since it could be expressed as like as a it could be expressed as multiples of each other, so then we could easily conclude from our previous analysis, yes, for the case of complex vector space, the CS inequality is always an equality. So it is kind of a corollary. So it is kind of a corollary from this particular observation that we did earlier. So the next 9 problem and the 10th problem, they are essentially based upon a concept known as the rank of the matrix. So they are based upon this particular term known as the rank of a matrix. So you have a matrix and then you have to find out what is the rank of the matrix. So let me first introduce how to, like, what is actually the rank of a matrix known as. So rank of a matrix can be found out by reducing a matrix. Suppose if you have an original matrix here, the first step is in reducing the matrix to a row reduced form. You have to reduce this matrix to a row reduced form, and then after that, from the row reduced form, you can easily conclude what is the rank of the matrix. So that is the very first step. So how can we transform a matrix to a row reduced form? We can, in order to bring down a matrix into a row reduced form, we are allowed to use certain elementary row operations. So the row operations are, the allowed elementary row operations are as follows. You can interchange rows. So suppose like you have a matrix, let's say it is this is the matrix. So in order to reduce this matrix to row reduced form, you are allowed to perform the following operation. You can interchange the rows. So what you can do is you can interchange R2 with R1. So the second row will go to the first place. Yeah. Second row will go to the first place and vice versa, and the third row remains as it is. So I have performed row interchange in the rows. Now the next allowed thing is multiply a row by a non-zero constant. So you can actually multiply a row to a non-zero constant. So that is like, suppose let's multiply the R2 with 1 by 4 of R2. So this is a non-zero constant. I am multiplying it with R2. So this is also allowed. 5 by 4, 6 by 4. So this is allowed. We are multiplying a row by a non-zero constant. So another allowed thing is that you can add a multiple of one row to the other. So what you can do is you can add to R2, you can add some multiple of the other row. So third of R1. So this is some multiple of the other row. I am adding to row 2. So with that change, what it will be, like thrice of R1 would be 3 into 1. So it will be 1, 2, 1, 4. Then let's multiply 4 actually. So if I multiply 4, then it's easy it will no longer be fractional. So 4 into R1, 4 into R1 would be like 5 by 4 plus 4 into 2. So it will be 8. So 37 by 4. So likewise we can change the third element also. It would be 6 by 4 plus 4. 22 by 4. So this is what you can do. So these three operations are allowed, and using these operations you can reduce a matrix to a row reduced form. Now the next thing is to discuss how does a row reduced form looks like. So we can't just perform any kind of operation and any kind of this allowed operation and just reach anywhere. So it has to be a row reduced form. So the row reduced form of a matrix has some rule. So these are the following features of the row reduced form. So if you have a matrix, then the leading entry of every row, they should be 1. So if this is the leading non-zero entry, so the non-zero leading entry is actually the non-zero entry, so it always has to be 1. There is an exception. There can be a row where every element is 0. So there can be such row where there is no non-zero element. So all elements are 0. That is fine. But if there is a non-zero element and that element has to be 1, the first non-zero element, the leading entry, it has to be 1. So that is the first criteria. So the column which contains the leading entry of some row must have no other non-zero entry. So this is the column which contains the leading entry for the first row. So the other elements in the same column, has to be 0. So yeah, so all of the other elements are 0. Similarly, let's say the leading entry in the second row always has to be 1. So this is the place where it should be, and all other entries in this column has to be 0. Now let us say that there is a leading entry in the third row which appears here. So all other entries has to be 0. Yeah. Now let's say there is a fourth row itself, and all of the elements are 0. So now here is no leading entry, but that is what the exception was. A row may have every element to be like 0. But if there is such row exists, then it must come at the bottom. So this 0 0 0, it can't just lie anywhere in the intermediate rows. It always has to be at the bottommost row. So that is what it is, like it is at the bottom of the matrix. So, and as you see from the property 3 says that leading entry moves right as we go down the row. So as we are moving from the first row to the second row to the third row, the leading entry 1 is moving right, is moving in the right direction. So these are the features of the row reduced form. So once you bring it down to a row reduced form, you can find the rank of the matrix. So the rank of the matrix would be number of rows. There are how many such rows which contains at least one non-zero element. So that would be the rank of the matrix. So in this, for this case, this is a 4 cross 3 matrix, but the rank of this matrix is 3 because the fourth row has no element to be like non-zero. It has all elements 0, so we don't count that row. So there are 3 such rows. So number of rows is 3. So rank for this matrix is 3. So this is an example. So suppose you have this matrix, then you perform several allowed row operations. So all of this allowed row operation, interchanging rows, multiplying a row by a non-zero constant, and adding a multiple of one row to the other. These 3 operations you perform like suitably, and then you bring it down to a row reduced form. So this is the matrix and this is a row reduced form. You can see all of the conditions are satisfied. The leading entry is always 1, and in the row containing the column which contains the leading entry has all other elements to be 0. So this is the column containing the leading entry of row 1, and you can see all other elements are 0. Similarly, this is the column which contains the leading entry of row 2, and all other elements are 0. Likewise for column 3 itself. So this is what is a row reduced form. And also you see the leading entry moves to right as you go from first row, second row to the third row. So that is the row reduced form. Yeah. So that is what you have to like bring it down to check the rank of the matrix. So we have this particular matrix at hand. So we have to perform row operation to bring it down to a row reduced form. So this is the operation you have to perform. So let us perform the row operation. First of all, what you have to make sure is like make the first element to be 1, like the very first element in the matrix to be 1. So that is what you should always keep in mind, because the leading entry of the first row is in the first column itself. So it is, if this matrix is A11 should be always, so this the dimension is 4 cross 4. So A11 always has to be 1 in the row reduced form. So since it is already 1 here, you don't need to bother about it. But in case if it was like some other value, some like 4, or let's say it was like -5, so what you have to do is multiply a scalar, multiply some constant to this first row so that it becomes 1. So in this case you would multiply it with say R1, you change it as R1 by 4, or here you change it as R1 is equal to R1 divided by -5. So that is what you have to do. For if had it been the first A11 was not 1, but since in this case it is already 1, so we don't need to have to bother about it anymore. So the immediate row operation is motivated by the fact that the column containing the leading row, containing the leading entry of that row, is all other elements in that column are 0. So we have to make sure that these 3 entries in the column are 0. So that is done by these 3 like row operations. So we are adding a multiple of the other row to our row. So we are the multiple of our row, like multiple of R1, we are adding it to R2. So this is one of the allowed row operation. Similarly, we are performing operations on R3 and R4, and we are making all the entries in that column to be 0. So we have done our we have done our operations with first column. Now let us check for the second row. So the second row leading entry again has to be 1. So that is why right now we are doing this operation to make this particular elements, because this will be the leading entry. So that is why we are making it 1. After that we are performing again the similar set of row operation to make the other entries of the column to be 0. Yeah, we are making the other entries of the column to be 0. So then what we have to do, like the next thing, so after we do this, we find out that the second row, all of the elements, none of the elements are actually non-zero, all of them are 0. So and they occur at the bottommost of the row. So this matches with the definition of our row reduced form. So there are like the leading entries in the first row, leading entry of the first row is at the left, and the leading entry of the second row is at the right. So as you go down, the leading entry moves to the right. So that is even matched, and the column containing the leading entry has all other elements to be 0. So that is also satisfied. So right now that since this is a row reduced form, so this is a row reduced form. So we can say that rank of A is equal to 2, because there are only 2 such rows which contains at least one non-zero element. Row 3 and row 4 contains no non-zero element. So only it is the first 2 rows which contains at least one non-zero element. So that is what that is why rank of this particular matrix is equal to 2. So our job was to reduce reduce a given matrix to a row reduced form, and then counting the number of rows which contains at least one non-zero element. So that is what is the motivation is behind finding a row reduced form. So the next thing is we have a system of equations. So this is the problem 10 is based upon three simultaneous linear equation. We have three variables here, and and we have three equation. This can be casted into a matrix form. So we can easily write it in a matrix form where this particular column vector contains the constants which appear on the right hand side. Yeah. And this column vector, it contains the variables, and this matrix is the coefficient matrix. It contains all the individual coefficients. So 1 1 2, 1 minus 1 1, 2 4 5. So when you perform the matrix multiplication, you'd get back the same expression which you have here. So that is why we could say that we can recast this system of equation as in a matrix form. So this is my matrix coefficients. This is a matrix of coefficients. Yeah. And it is denoted by m. And this is my constant, and this is my variable. So what is augmented matrix? So in augmented matrix is you have the matrix of coefficients. This is the matrix of coefficient, and then you augment. You augment the you concatenate. You can say concatenate the constant vector as a column of other vector, as a column of another vector, as a column of the original matrix. So we could do this. So this is my augmented matrix actually. So this particular thing is my M. This is the matrix of coefficient, and this is the augmented matrix. So we have to find the rank of both of this matrix, of both M. So this has the dimension of 3 cross 4, and this is 3 cross 3. So what is the rank of this, and what is the rank of A? What is the rank of augmented matrix, and what is the rank of the original matrix? So in this case again we start with this same the same procedure. Like we first write the augmented matrix, and again we verify whether the first entry is 1 or not. It is 1, so we don't need to bother much about it. So we immediately go to the row operation, that is make other entries in the same column to be 0. So we perform row operation and achieve it, and then perform this particular row operation that is multiply by some multiplicative factor of a row, and then make the leading entry to be 1. So we multiplied it by minus half, and that gave me this particular factor. It made it 1. So after that operation, our next task is to make all other entries in the column to be 0. So these two to be 0. So that is how we achieve it. Yeah. So that is how we achieved it, and ultimately we are reduced down to this form. So this is the form of the row reduced form of the augmented matrix. So we started with this and we reduced it to a row reduced form. So right now here what we see is the rank of the augmented matrix is 2. Rank of the augmented matrix is 2 because the third row contains no non-zero element. And if you have to find the rank of M, so you have to look only in this section. So again the rank of M is also 2 because the final row has no non-zero element. So that says the rank of the augmented matrix and the rank of my original matrix, that is the matrix of coefficient, is both 2. But there can be cases where rank of the augmented matrix can be different than the rank of the original matrix. So imagine after performing row operation, we get something in this 0 or in this location we get 1. So this is a non-zero element. So what we say in this case, the rank of A is 3, but rank of M continues to be 2. So that is what one possibility it may arrive. So that actually says that my rank of the augmented matrix can be greater than or it can be equal to the rank of the matrix of coefficient. So this is one of the corollary that we get to see from this particular exercise, that it can be equal to, in this case it is equal to, but it can also be possible that it is greater than, like it can be greater than the rank of the matrix of the coefficient. So that is what this exercise could do. So we had solved 2 problems that helped us to find out the rank of the matrices. Yeah. So like, since this is not a live session, so in general in live session I would let the attendees to ask question regarding any contents you have, any doubt in the contents you have that has been discussed so far. So moving over to the summary, brief summary of what I did, what I discussed so far. So the very first thing that I started with is the triangle rule of vector addition. So in that I describe a vector is something which has a magnitude and direction, and the triangle rule of vector addition was given by this. Suppose there is a vector AB and BC are 2 such vectors, then the resultant of AB and BC is given by the AC vector. So that was the triangle rule of vector addition. So this particular question, this particular concept helped us solve the entire complete one question, provided with the fact that parallel vector has same direction as the original vector, but its magnitude is can be less or greater than the original vector, but they have the same direction. So that was the both of this concept helped me solve the first question. Then from the second question to the 5th question onwards, it was required to check whether some set does it forms a vector space or not. Yeah, we have to check whether a set forms a vector space or not. In order to check that, what we did is we referred to 4 criteria that must be satisfied by this set for it to form a vector space. One property was closure under closure rule. So there were 2, one with the vector addition, so it should be closed under vector addition, and it should be closed under scalar multiplication. So those are the 2 of the rules, and the third rule was existence of identity. So every element, the vector set should have an identity element, and that identity element should lie in the vector space itself. And the third was the existence of inverse. So every element again should have an inverse that is lying in the same set itself. So given this particular set S obeys all of these 3 conditions, we concluded that it indeed forms a vector space. Next thing is we discussed about something called when an inner product forms a legitimate scalar product. So that was the next condition that we checked. So it had to again satisfy some set of rules. Another one is suppose x and y are 2 vectors, then it had to satisfy this particular rule. And the second condition was the distributive property. So z had to distribute to the x and y respectively. So that was the linear product, the inner product definition should obey this condition also. And the third one was positivity, that is has to be inner product of a vector with vector itself has to be greater than 0. So given the inner product definition or obeys all of this criteria, then we could conclude that this is indeed forms a the scalar product. Now the Cauchy-Schwarz inequality was given x and y are two vector, then the following condition has to be met. So this was the Cauchy-Schwarz inequality criteria. And then we also saw that if the vectors could be expressed as a linear, they can be expressed as a multiple of each other, then this inequality reduces to a equality. That was a special case. So now the linear dependent vectors are those vectors which do not depend on each other. So they cannot be expressed as a multiple of one another. So if they can be expressed as that, then they are not linearly independent, they are linearly dependent. So that was with the linear independence of vectors. Then meanwhile we also discussed about orthogonal vectors. In that case, two vectors being mutually orthogonal means their inner product is equal to 0. So that was with the orthogonal, mutually orthogonal vectors. And then we came to discuss about the how to find the rank of the matrix. So in order to find the rank of the matrix, it was important to reduce a matrix to a form which is known as the row reduced form. It was the row reduced form, and then this row reduced form, from looking at the row reduced form of the matrix, we could calculate the rank of the matrix. So how to go about from a matrix to a row is row reduced form is being achievable by performing some elementary row operations. So following such suitable some row operations, we can reduce a matrix to a row reduced form, and from the row reduced form, if we count how many number of rows are there that are containing at least one non-zero element, so those many number of rows would be known as the rank of the matrix. So that is what we discussed so far. So if this matrix is A, so we can find out the rank of the matrix. So this is all that we discussed so far about the vectors, and slightly we got introduced into the various properties in the matrix operation. So that is all for this session. So thank you everyone. So I would have taken doubt if this session was a live session, but in next tutorial session, see you all in that. It will be a live session, and in that case, I'll be ready to take doubts and clear all your doubts. So see you all in the next tutorial session again on Sunday from 4 to 6 p.m. Thank you everyone.